So, welcome to the fourth of our optional examples classes on definitions, proofs and examples. We've been adding questions gradually, so I'm up to 58 questions on the definitions, proofs and examples question sheet, which we are selecting questions from. And we're going to start with a definition for a change. Okay, so what does it mean to say that a sequence of real numbers tends to infinity? Now, we don't count this as convergence in this module. It's some sort of a limit or divergence to infinity or plus or minus infinity. But it doesn't count as convergence in this module. So if you write yn tends to infinity, it's one particular way of diverging. Yn tending to minus infinity is another way of diverging, but then there's various kinds of oscillating sequences as well that also diverge just because they don't converge. So I'm going to let you think for a couple of minutes about whether you could write down a formal definition of what this might mean. Now, there are actually several equivalent definitions you could try, but I thought I'd see if anybody could try and write one down with quantifiers involving for all numbers m, and something about existing a capital number n, and something about little n. The usual sort of thing you have to do with sequences if you want to write a formal definition. I want to see if anyone can think out a definition that might work for this. Or you can use absorption if you like. If you like absorption, you can talk about which sets should absorb the sequence if you want the sequence to do one of these two things. Tend to plus infinity or tend to minus infinity. Note that infinity is plus infinity for us. It's the one at the right-hand end of the number line, the way we normally draw it. Okay, so I'll pause it there and let's see whether people got some ideas. So let's see various ways of doing this. I've seen a correct answer already, though it used an epsilon for something that should be sort of big. So I wouldn't normally use epsilon for a big number. The strength here of this definition is that no matter how big your number, you should eventually end up to the right of it. That would be for the first one. And no matter how negative your number, you should eventually end up to the left of it. That would be the second one. So let's get rid of that arrow. So yn tends to infinity as n tends to infinity. If and only if. Here's one of the standard definitions. For all m greater than 0, we could just take, it should be a real number greater than 0, of course. That's our standard assumption. There should be some point, a big capital letter, big capital N in a natural numbers, and that's going to be big enough so that when you get beyond that point in the sequence, you should be further to the right, or at least as far to the right as m. So that's one. Actually, it's the big positive real numbers m that matter, but you can do this. You can get the same effect by taking all real numbers m. The negative ones don't have any effect on this because you're interested in large positive ones. But it's the same as for all real numbers m. So it's the same otherwise. And if you want to use absorption, it says for all m in R, the interval from m up to infinity absorbs the sequence. That contains the whole of the difficult bit. The exists capital N, so that from that point on you're in the set. That's what absorption takes care of for you. So if you like absorption, you can make the statement less complicated this way. Of course, hidden inside the absorption is the there exists a capital N, so that for all n greater than capital N, you're in that interval. So after a while, you're stuck to the right of m, and then after a bit further, you'll be stuck to the right of something bigger, and then eventually you'll be stuck to the right of a billion, and then a bit later you'll be stuck to the right of a trillion, and so on. And that's what forces you to tend to infinity. And 2 is similar. Yn tends to minus infinity, and then tends to infinity. If and only if, well, you can use the m smaller than naught or something. I'll just do the all m in R again, but this time it's the negative n that's interesting. So I say for all m in R, but you should be interested in the negative n this time. There exists an n in n such that for all n greater or equal to capital N, we have, and this time you're less than equal to n. If you like your m to be positive, then just use minus m instead of m here. It makes no difference to the definition. So in fact, let's have an extra page. So I'll point that out. That's if and only if for all m in R there exists an n in the natural numbers such that for all n greater or equal to n we have xn less than or equal to minus m. If you like that one, the nice thing about that one is you can use the m greater than naught version for that. Remember, it's the getting to the left of very negative numbers that matter. So I could use if and only if for all m greater than naught there exists an n in the natural numbers such that for all, and you may not want to write all this stuff down, you can say dot dot dot. If you're going to use minus m, then you should use m greater than naught. If you're going to use m, you should use m smaller than naught. If you're going to do one of these one-way ones. And I'll give you an absorption version again, if and only if for all m greater than naught, the interval from minus infinity up to minus m absorbs the sequence xn. It's eventually to the left of any given point, and if you go far enough, it'll be less than or equal to minus a million, and if you go a bit further, it'll be less than or equal to minus a billion. A bit further still, it'll be less than or equal to minus a trillion, and stuck there, and so on, and that's what it means to tend to minus infinity. Okay, so that gives you formal definitions that you could work with. I will now give you for free, to help you with the next question, here's a standard fact you could use. If yn tends to infinity as n tends to infinity, then every subsequence of yn also tends to infinity. So that's just like the usual thing that if a sequence converges, then every subsequence also converges to the same limit. Well, this also works for this kind of divergent sequence. These special kinds of divergent sequences, which happen to tend to one of the infinities, every subsequence will tend to the same infinity. So if yn tends to infinity, then every subsequence of y will tend to infinity as well. And the same for minus infinity. If yn tends to minus infinity, then every subsequence of y will tend to minus infinity as well, as n tends to. As you go along the subsequence. And that helps with the next question. I'll give you some other facts that will help you with this one. Now, here are 3 statements you can say about a sequence of real numbers. One of them is that the modulus tends to infinity as n tends to infinity. Now, that doesn't tell you that xn tends to plus or minus infinity, because it could be something like minus 1 to the n times n, which oscillates wildly and doesn't tend to either of the infinities because it goes -1, 2, -3, 4, -5, 6, and so on. That doesn't tend to infinity, and it doesn't tend to minus infinity, but the modulus of it will give you 1, 2, 3, 4, which will tend to infinity. So that's the sort of sequence we're talking about in a sequence where if you take the modulus of the terms, you get a sequence tending to infinity. And that was A. B has no bounded subsequence. That means every subsequence is unbounded. And C has no convergent subsequences. That means every subsequence is divergent. But it doesn't mean that could be an oscillating divergent. It just means every subsequence is a non-convergent sequence. So it's not obvious that these things are equivalent to each other. So this is quite a little interesting result. And things that you can use to help you are, let's see, Boltzano-Weierstrass. If you remember what Boltzano-Weierstrass theorem says, Boltzano-Weierstrass says every bounded sequence has got at least one convergent subsequence. So that's going to help when you're working what's going on with B and C. You can quote that every convergent sequence is bounded, but not conversely. That's a one-way implication, which helps you somewhat with B and C, but bearing in mind that bounded sequences don't have to be convergent, you have to do a bit more work to get the other direction. And what else could you use? I've got that if you tend to infinity, then every subsequence tends to infinity. And I'm going to give you another one, but I can't remember what the other one was for the moment. I'll probably think of it in a minute. So let's see how you get on with that for a start with, and I may give you another hint in a minute. Okay, so I remember now. You're allowed to use for free that if you take a subsequence of a subsequence, you've still got a subsequence of the original sequence. Okay, I'm going to prove some of the easy bits for you. I'll do A implies B and B implies C because they're the easiest ones. So, we need, let's do A implies B to start with. So, given that mod xn tends to infinity as n tends to infinity, I've already told you that every subsequence has the same property. For every subsequence, xnk, we have mod xnk also tends to infinity as k tends to infinity. Because you're just taking, it just can only go to infinity faster than the original because it was already tending to infinity. You can think about that as a little exercise for more details, but I accept that as true. And a sequence that tends to infinity cannot be bounded. And that's the subsequence goes from k equals 1 to infinity. If it tends to infinity, it can't be bounded. So that does that one. And for B implies C, if I've got the logic the right way round, this is just because every convergent sequence is bounded. So if you've got no convergent subsequences, if you've got no bounded subsequences, you can't have any convergent subsequences either. Because if you did have a convergent subsequence, it would be bounded. New page. We've got no bounded subsequences, and Xn has no convergent subsequences either. Okay, so that does A implies B and B implies C, and now you have to figure out the best way to finish. Can you do C implies A, or do you want to do C implies B and B implies A, which I think might be the best thing? And how do you want to do B implies A? Maybe you should look at not A implies not B. So let's have a look at, so I suggest finish with not A implies not B and C implies B. And that will actually do it. Not A implies not B will give you B implies A, so they'll be equivalent. And C implies B will mean that B and C are equivalent, and you're finished. So slightly more implications than you might usually expect to have to prove, because you can sometimes prove them in a cycle. A implies B, B implies C, C implies A. But I think that's not quite so easy here. You may find you can do it. Okay, let's see how you get on with that. Okay, it's time I did some of these for you. Let's have a look at not A implies not B. You have to be very careful with this one, because you have to be worried about things like oscillating sequences, like -1 to the n, which doesn't tend to infinity, but nor does it converge to anything else. So you can't assume it does converge to something just because it doesn't tend to -infinity. So let's have a look at, not a very good example, that one, because if you take the modulus of -1 to the n, it does converge to something. But you can still arrange, if you look at the sequence that goes 1, 2, 1, 2, 1, 2, then that one has got a modulus that doesn't tend to infinity, but nor does the modulus of that sequence converge. So the sequence 1, 2, 1, 2 gives you something to worry about. Okay, let's have a look at not A implies not B. So we're given that it's not true that Xn tends to infinity as n tends to infinity. Or in other words, it's not true that for all m greater than 0, the interval m up to infinity absorbs the sequence, for example. i.e. again, there exists an m greater than 0 such that it should be it was modulus xn, right, tending to infinity, so let's just fix that. And this last sequence that doesn't get absorbed is mod xn. And I need another bracket, but never mind. Run out of room. There has to be an m greater than 0 such that this interval doesn't absorb the sequence. And what I wanted to really write up there is that sequence as n goes from 1 to infinity. Now, what does that really mean? You absorb it. To absorb something means that there are at most finitely many terms of the sequence outside it. To fail to absorb something means there are infinitely many terms of the sequence outside it. So, there are infinitely many n in the natural numbers that. Get rid of that. What I want is that. With mod xn not in the interval from m up to infinity. So that's, in fact, the correct negation of mod xn does not tend to infinity. Mod xn does tend to infinity. Negate that, and you get there are infinitely many. The sum point. This is there exists an m such that this happens. That's this last bit, about the not absorbing for this n. So for such m, there are infinitely many xn, mod xn. Mod xn, if it's not between m and infinity, it's got to be between 0 and n. And infinitely many means we can choose an n1 less than n2 less than n3 where it's true. Natural numbers n1 smaller than n2 smaller than n3. Just picking out these infinitely many n where this thing is true. And modulus of x and k has to be less than m for all k. That's just because the modulus isn't in the interval from m up to infinity, so that forces it to be, the modulus has to be less than m for those ones. And that, of course, is a bounded subsequence. So that gives you not B. Let's try it again. So that was not A implies not B. Now, there's only one left. We wanted C implies B. And I've changed my mind. I'm going to do not B implies not B, not C. I think that's easier. So given that B fails, that means xn has got a bounded subsequence. And I'll use different notation this time. Xn has a bounded subsequence say yn. What I really want is to get a convergent subsequence. So what could I use? Any suggestions? Sorry? Which theorem?
Every subsequence of a subsequence
is a subsequence. That's good. Yeah. So if we do manage to find a convergent subsequence of this, it will also be a convergent subsequence of the original. Okay? Now, how do we know that this sequence, yn, has got a convergent subsequence? Yes? Baltzar-Weierstrass. Yn is bounded. So by Baltzar-Weierstrass theorem, Yn's got a convergent subsequence, say Zn. But now Zn is a subsequence of yn and yn is a subsequence of xn. So Zn is also a subsequence of Xn. So C fails. It does have a convergent subsequence. And we have now actually finished. So you may have to go back and think about all the things we've done to convince yourself we've finished. You can now deduce all of them from each other. Okay, that was hard work, wasn't it? You know, I think we're just about out of time, so we probably better stop there.